recording. We are going to solve a linear system of differential equations. Okay. And we're given initial conditions as well. And then we're going to solve this initial value problem and then sketch the trajectory of the particle. All right, let me give you a moment to copy this down. Okay, so we have two differential equations, a linear system of two differential equations. We're given two initial conditions here. Okay, and so like you might have seen in if you've taken 282, math 282, you might have seen like dx dt, okay, and dy dt. Okay, you might have seen a system of differential equations like that. Well, we're using dx1 dt and dx2 dt only because, we allow it for the fact that you could have, more than two differential equations, right? So, okay, what is the first thing that we are going to need to do in order to solve this initial value problem? What's the first thing that we are going to have to do? Well, we're in chapter 5. And in chapter 5, what do we always do? What do we always find? That's right, eigenvalues, Justin, and then that's right, Eleanor, and of course eigenvectors. So in order to find that, we need to identify what is the matrix A. So for this problem, what would the matrix A be? It's going to be a 2 by 2. What's going to go in the first row here? What numbers? Now, obviously, I have to look at the differential equations. Remember, this can be represented as x prime of t equals a times x of t, right? So what's a going to equal? What's the first row going to be? What numbers? That's right, Nafani. 4 and -5. And what about the second row? That have to be -2, good, Nafani, and +1. Okay, so again, if you think, and I'll just rewrite it again here, x of t equals, I like just a little more space to write it out. So this was right, what I wrote here. I just want to have it written more nicely here, you know. So, sorry, x prime of t equals a times x of t. This is x prime of t here. And then a times x of t would come from the right-hand side. So, okay, all right. So let's begin then. Because this is new to you, I define, again, it's obvious what the vector x prime of t is. It's obvious what a is and what x is, the vector x and x sub 0. Okay, and we're going to use the MATLAB command, this MATLAB command, eigsim of a. Okay, and this will yield the following eigenvalues and eigenvectors. And therefore, based on what you just learned, and I'll give you a moment to catch up here. Obviously, it takes some time to copy this. Based on what we just proved before our break here, the general solution to the linear system of differential equations is given here. It's the linear combination of the two eigenfunctions. All right, let me give you a moment to copy this down. Please let me know if you have any questions. Okay, and of course, this is actually example 2 that we're doing in the book, just to make you aware of it. But okay. Okay, so now we get to this stage here. We get right here. This is our general solution. What are we going to do now? What must we do now that we have our general solution to our linear system of differential equations? What do we do now? What comes next? That's right, we have to, very good. We have to solve for the constants C1 and C2. Okay, we have to solve for those parameters there. And we're going to use our initial condition. Okay, the initial condition was that x1 of 0 equals 2.9 and x2 of 0 is equal to 2.6. All right, so if we're good, I'll move to the next page if there are no questions. Okay, well, all right, so again, this is the initial condition vector, but we're going to, of course, then substitute in t equals 0 for the t value. Okay, and so, I mean, you end up with this vector here equaling the right-hand side. Okay, and again, we put in t equals 0 in the right-hand side. And now you end up, I mean, this is a vector equation here, and we're going to solve that vector equation. And I used MATLAB to help me. But of course, with this system, you know, by default, MATLAB is going to give you decimals. But if you use format RAT, if you use that command that stands for format my answers as rational functions, you'll get fractions. Now, sometimes the fractions are kind of ridiculous. You know, if you got something really ugly that isn't if you get answers that are ugly and can't be represented well by fractions, you format RAT isn't that helpful. But in this case, by doing this and using MATLAB, you'll see that C1 equals -3/70 and C2 equals 94/35. Now the book, incidentally, oddly enough, the 94/35, they represent it as 188/70 in example 2. But, you know, either way, it's okay. My MATLAB would accept either way. But you always have to be careful on these problems right? To read the instructions, to make sure that you're giving MyMathLab the answer once. For exams, you have to read the instructions, make sure you're putting it in the right form. Okay. And always, if you can get nice fractions, usually MyMathLab wants that, right? If you can get nice, clean answers. So. Okay, let me know if you have any questions. All right, are we ready to go to the next page? Let me know when you're ready. Abby's good. Okay. Natalie's good. Okay, good, good. Benjamin's good. Catherine's good. Okay, all right, very good. Well, all right, so then here's the general solution, or no, not the, here's the solution to the initial value problem. And then the trajectory, I thought there was a lot of nice information in the paragraph or in the example regarding the figure, regarding the trajectory. So I just, included all of it. And so, I mean, it's up to you whether you want to copy down, this here, but you have the time to do it if you want. So let me give you a few moments here. Sorry, I guess I didn't have my volume on there. Hold on, I have to do this again. Sorry, hold on. So e to the negative t, as t gets large, e to the negative t approaches 0 as t goes to infinity. Okay, and that means then that this entire second portion of the solution for xt, and what is xt? Remember, xt is a position vector. It gives the coordinates for the trajectory at some value of t. So this entire second half of x of t will approach the 0 vector as try to make that look good. I can make it look good. As t goes to infinity, okay? As t goes to infinity. This means then that when t is large, only the first portion of your, this part here, only that portion remains. And what is that? What is that? Well, negative 3/70 is a scalar, and e to the 6t power for some value of t will be it'll be a number, and then you're multiplying it by that vector. So as t gets large, the position of the trajectory is going to equal some multiple of the eigenvector v1, negative 5,2. And this is why if you notice in the trajectories, and well, what they've done is they've drawn the initial value x sub 0, which was x sub 0 was what? The vector x sub 0 was equal to 2.9 and 2.6. So that's right here. They draw a lot of trajectories. Okay, but our trajectory does this. All the trajectories, as t gets large, move away from the origin. Our trajectory does that. And if you notice here, let me just phrase it the right way here. The eigenvector v1, which is given by negative 5,2, that's right here in the picture, right there. Here is the line that passes through the origin and through eigenvector v1. So you see here how the solution, okay, x of t, which we have up here, okay, we found what x of t was, the position vector, but the solution right here, right in red here, I'm trying to, and I'll be done in just a moment here. That solution is basically looking parallel to the line that passes through the eigenvector v1 in the origin. And that's because as t is large, that's the only portion of the position vector that's left. The other part disappears, right, as t gets large. And all of the trajectories, as if you look at the arrows, signify that t is greater. All the trajectories take on paths that are parallel to the line passing through the eigenvector v1 and the origin. Okay, so the direction of greatest repulsion, therefore, the direction of greatest repulsion here is the line through v1 and the origin. Okay, and the direction of greatest attraction would be the line through the other eigenvector in the origin. Okay, so are there any questions on this example? And the origin's a saddle point too. Are there any questions at all? Who's feeling reasonably comfortable? Who's feeling reasonably comfortable? Maybe give a few chats if you're feeling reasonably comfortable. Okay, Eleanor is, Catherine is, good, Benjamin. Okay, Naima, Natalie, wonderful, wonderful. Well, you learned a lot of good things here. Lewis is too, and Natalie is too. All right, let me stop the recording then.